Professor Dr. Magistral decided to deliver conference here at Faculty of Sciences because he's raised plenty of students, and I know I have learned that he is initially and mainly professor involved in teaching and also in high quality research. Then I would like to welcome Professor Dr. Dag Hanstorp to the Faculty of Sciences to deliver conference with the series Physics Across the Atlantic. I am aware that there is a long-term collaboration with one of the important Professor Hans Pivotal driving this collaboration, this internationalization of National Autonomous University of Mexico, and in this case, Faculty of Science Center for Physics and also Institute of Physics. So, Professor Hanstorp, welcome and thank you for accepting this conference in this Faculty of Sciences. Thank you.
Buenas tardes, mi nombre es Enrique Cabrera del Instituto de Ciencias Físicas. Algunos de ustedes habrán recibido los correos invitándonos a la convocatoria de este intercambio. Some of you might have already received the announcement of the opening for this exchange. If not, it's coming out pretty soon. Why I'm here is because this collaboration of internationalization between the University of Baltimore and UNAM started 10 years ago. And we have right now sitting 4 students here that have come back to this exchange. So if you want to talk at the end, if you would like to participate, you're welcome. Of course, Professor Hanstorp, as you see in the title, he likes to talk about PATA. We used to call it PATA, P-A-T-A, which is the Physics Across the Atlantic. And it started as a series of conferences on Zoom between colleagues at the University of Baltimore and colleagues here at UNAM. So this exchange after 10 years has been so fruitful that now UNAM, of course, has given to Professor Hanstorp the honor of honoris causa, his second honoris causa. So you can call him Professor to the Q, if you want. Without no more words, please, at the end of the conference, if you have questions regarding the exchange or you would like to participate in academic research, please come and join us and discuss with us over here. And without no more ado, I would like to welcome Professor Hanstorp to deliver his PATA talk. Thank you.
Thank you very much. Hello, all. Okay, so the title of my talk is Physics Across the Atlantic. And as you heard, the reason I come here to Mexico this time is that I got this very honorable title, honored Doctor of the Casa. And I will here present a little bit what I've been doing on my own research and also in collaborations with UNAM. And just to point out where I come from, Mexico, the Gulf Stream, if you go down to Gulf of Mexico, get on a raft, and just wait for a month or two, you have 25% chance of ending up here. And that is Gothenburg, where I'm from. And Gothenburg is in Sweden, it's like the industrial heart of Sweden, the big harbor. So like 1 million people living in the area. So this is the entrance, and outside is this very nice archipelago. Just a few words about Sweden. Population is 10 million, so half the population of Mexico City. The area is 1.5 million square kilometers compared with Mexico's about 2. And I just put this map of Sweden. Green means forest. As you can see, it's basically mainly green. And then north, we have some Arctic in the mountains. And then the two yellow spots here is the agriculture part. It's on the 57 degrees, it's very high north. If you go to America, you look up to the middle of Hudson Bay. But due to the Gulf Stream, the climate is cold but not Arctic. And the collaboration that they operated is called the Southern Exchange Program. And just to explain what this means, first have a look on the two names here. Linnaeus, Carl von Linné. He was the founder of botany. So it was just before Darwin. And basically he systemized the whole plant system, gave the name with a family name, a specific name, and two Latin names. And he was a big scientist, and he had a lot of students. He actually felt pretty big about himself because he called his students his disciples. And he sent them out in the world to explore. So that is kind of the origin of the name, the half of the name. The other name is Olof Palme. He was maybe the most famous politician in Sweden. He was a social democrat, and he had a big heart for the third world, and he's had a lot of collaborations all over the world and brought a lot of people from Africa, from Latin America, from Asia to Sweden. So, and actually he visited Mexico in 1984. Tragically, he was assassinated on the street in 1986 in Stockholm. So this exchange program has two parts. Linnaeus, that means that we send out Swedish students to anywhere in the globe, and the Palme is that we bring students to Sweden. And we have been going on since 1914. And actually, I just give a very short story of how this started. In the late 90s, I worked with Dr. Alex Aguilar, who used to have in the audience here. He was a scientist at ALS in Berkeley, and I came as a researcher to do experiments with him. We spent many times together and started to talk, and we saw we have a common interest in our work. So we decided to set up a program. We needed some funding, and then I saw this ad about this Linnaeus pilot program, but they didn't sponsor going from Sweden to USA. That was not part of the program. But then Alex said that I have a colleague here at UNA, which is Professor Antonio Juarez. So they said, okay, let me set up an exchange between Gothenburg and UNA to work on this program, to work at ALS. We got the funding, but 1 year, just when we got the funding, then basically the ALS had a big shutdown in the economy, and Alex left to go to industry. So then me and Antonio started to proceed with this program. Then quite soon after, Dr. Emilio took over the collaboration, and we're running this since 2014. So if you have to say, this is the teacher changes that we have within the framework of this program. So it's 5 professors from UNA that come to frequent visits to Gothenburg, and 11 professors from Gothenburg University have come to UNA to take part in research. Which is, of course, a very important part, but even more important is actually the student exchange. And we actually have had 25 UNA students who have come to do their master projects, to spend a year in Sweden, and 11 students from Gothenburg have come to UNA to do work in research support projects. And it's quite interesting in a topic like physics that we actually, when I summed this up, there was 18 female and 18 male students in this, which I think is unique for physics. So this is now my projection of the globe to see here. So we have Mexico here, we have Sweden here. And these dots here, I managed to, before I came here, I tried to get in contact with all the students. Out of the 36, I got in contact with 35. And then with each dot here is the location of those students at this time. And here we see in Mexico, we have 6, and 4 of them are sitting here in the audience. I'm very happy for that. Black dots are the Mexican students that have participated, and the blue dots are the Swedish students that have participated. And for each of those dots is a very special case, and I just picked two. This is Israel Rebolledo, and he just stated that when he celebrated me, the program really changed my professional personal life. I will be always grateful for the leaders kind of program. So he came to do a master project, then he got a PhD in Sweden, and now he's working at the main research institute in Sweden in metrology. And just to pick one going the other way is Amelia Flattersson. She is an oceanographer firm, and she stated that opportunity to travel to Mexico really changed my career path. Now I'm in Mexico again as a PhD student in oceanography, studying Honolulu in Gulf of California. So, and I can always have time to eat. So it's a unique career changer that have the opportunity to do this international exchange. So that's really what I'm the most proud of in the whole career, what I'm doing, but to be able to make this possible for all these people. And just to finish this kind of introduction, this was one time when I came, and this was about this time of the year, and the first snow fell. So me and a colleague went up to our garage and found all the snow equipment, so we went out to play in the snow. It was very time the first time I seen the snow. It was a group of Mexican and Indian students that took part in this event. So that's why I'm here. And now I just want to say, okay, go into the research I'm involved in together with Mexican and Swedish students and colleagues. And my main topic of research is spectroscopy of negative ions. So it's atomic physics where we study atoms with one extra electron. But I do also other things. And one thing is optical manipulation. So basically using light to trap and move around particles. And I just want to see, hope this works. Yeah, so this is a small experiment. What you see is a laser beam. This is like 3 centimeters. And then we spray, and this is a bicycle lubrication oil that is falling down. And you can see there's oil drops everywhere. You only see them when the light is. And if you now wait a little bit, you can see what happens. There one oil drop hitting the laser beam, and now the photon is bouncing off the droplet, and the pressure, the photon pressure is pushing up, completely compensating gravity. So we can hold the droplet, and this oil is not evaporating, so we don't know how we can trap it. We want to hold it evening for at least 10 hours. And of course, this can be a lot of research done using this, and we can control particles in a good way. Second topic I work with is that we have femtosecond lasers that is extremely short pulses with extremely high intensities. And here we show you a small video. This is have to do with combustion. So this is a question when you do combustion like a diesel engine, then you inject the fuel, but then you want the fuel to atomize to be as small as possible when the ignition comes. And this has been defined, and of course in Gothenburg, Volvo is a big place, and this is a very important thing. For the diesel, they have made this very nice and efficient, but when it comes to biofuels, they evaporate in a different way. And we just had a short project, and in this case, we took this is an oil drop that we hold in an acoustic tracker. This is about 1 millimeter size. Then we focus the femtosecond beam in the center of a single pulse, which basically means that we boil the liquid inside the droplet. And no. There. And now you can see now how this evaporation just grows and grows. So this is image with a high-speed camera. The camera can take 600,000 images per second. And then we can study in detail how this droplet evaporates. You can change the conditions to see how we can make this in an efficient way. My fourth research interest in physics education research. And this was something that I was asked to do during COVID. When COVID hit, students were sitting in dormitories alone, didn't need anybody. So head of studies came to me and said, can you do a physics lab that follows the restrictions of COVID? You have to be outside, people have to be separated. So then I went to the football field and we bought a drone, and then we line up all the students here, and here you can see two loudspeakers that send out 440 hertz, just a single tone. And then we ask the students to just walk around and place themselves on the maximum. And basically now the students taking part in this can now reconstruct the interference pattern. And as you can see now, we sorted the line a little bit. And you can now see, so here's like the first maximum, here are two maximum, and here and here. I was in the shade because when we did this, I asked them to find the maximum, but as an experimentalist, I should have told them to find a minimum instead. Because it's much easier to see when the sound disappears than when it's a maximum, because the maximum will go away a little bit, it's still pretty high. So this was actually repeated on a big football stadium with 400 kids of the age of 10 years old. And you can say you get maybe the same pattern, but you get more noise because 10-year-olds are more difficult to control. A lot of the kids move around more independently than what they were instructed. So that's my interest, but the main part of this talk, I will focus on this one. So then I just start negative ions for an atom with extra electron. And then go back to new scientists. And in 1973, on a cover it says all negative ions are free. And if you Google negative ions,
there's a very interesting way you could boost your mood and actually become healthier through negative ions. You ever wonder why you feel better when you're next to a huge waterfall or you walk into a forest crashing into the rock? And there's a common denominator with all those items I just talked about, and that would be negative ions. There are a lot more negative ions going on.
I don't know if you hear, but he said on those four places, the common denominator is there is more negative ions in the forest, in the waterfall, than in other environments. And this person claims that it should be very happy for you. And here you can see his conclusions that basically everything you get a better breathing before anything, you sleep better, your mood is better, stress goes down. I mean, it's a perfect thing. So of course, obviously, you should study negative ions.
There's a very interesting.
But now can I do from the atomic physics point of view? Okay, you have an atom here. You see, let's assume it's sodium, 10 protons, 10 electrons. This is a neutral system. And if you have an electron, there's basically no attraction. But if the electron comes close, basically the electron cloud will push to the other side. And if it's pushed to the other side, it can bind. And it can get a very, not a fragile system, is not bound very much. And if you compare now for an atom, you get the outermost electron in sodium, the potential of the electron goes away, is 1 bar. But this basically is an induced dipole. And that will actually scale as order to the 4th power. So it's only this electrocorrelation or polarization that keeps the negative ion together. And that's the main reason why I was thinking about the interesting to study. And if you then look on the energy level diagram, I mean, a typical atom have ground state, you have a lot of exciting state, you have a series of reverse states. For a negative ion, you typically only have a single state. And yeah, this is what the affinity to the binding energy is about 1/10 of the binding energy of a neutral system. That makes them very unique. And actually, if you the potential here can actually be shown that this is very simplified early in the quantum physics class. They say one of the square well potential with finite width, which very much mimic the properties of negative ions. So they're very good model system as well. So then I would say, just to see that if they are important or not. Well, if you take this, if I ask students, why is the sun yellow? Well, this was actually explained by Wilt in 1939. Because when you study physics, you study nuclear physics, you learn that in the interior of the sun, you have millions of degrees of Celsius to get the fusion running. But the outside of the sun is only 5,700 Celsius. And that is the temperature you see. But the question then is, why doesn't the radiation, the black body radiation from the interior of the million Kelvin come out? And so basically, what we see is this 5,000 Kelvin, which corresponding to that we see the visible spectrum of the sun. But the reason that it's 5,780 is actually the occurrence of H minus in the solar atmosphere. Because if I look on the, in the solar atmosphere, you have H2, you have H, you have a little bit of helium, you have H plus and H minus. All the other ones, H plus, helium, doesn't absorb visible light. But if I look at the energy spectrum of hydrogen, you have a 30.6 CD binding of hydrogen, whereas the affinity of H minus is only 0.75 E, which basically means that all radiations that have wavelengths shorter than 1600 meters is absorbed by H minus. So actually what's happening is that the radiation from here will be absorbed by H minus that recombines, and then what we see is the re-radiating from the surface of the sun. So if it wasn't for H minus, I wouldn't be standing here, you wouldn't be sitting there, because the Earth will not be habitable. Because we have a lot of energy. And here you can see actually the absorption spectrum of H minus, where we see that all the visible light is strongly absorbed in the solar atmosphere. Okay. So then, with that I say, I think they're interesting to study. When you come to when you want to study them, there's a little bit of a problem, because if you want to study H plus, you can say it's easy. You take the hydrogen and whatever brute force, high temperature, and you cannot react out. You say it's bang in the gun. If you want to make H minus, well, then you have H, and then you should gently get an extra electron sitting there. So you have to get that sitting there, but it's very loosely bound. So basically, any disturbance will just make it go away. So it's kind of more complicated experimental, that they're difficult to make and easy to destroy before we even have time to study them. So with that, summarizing the introduction of negative ions, why I think we should study them? Well, I think we can have it's very good to benchmark electron correlation theory. And as I said, they are good model systems, and they appear in many environments. I mentioned one, the solar atmosphere. They've also been found in the atmosphere of Titan. So astrophysics is a big thing now to search for negative ions. With that introduction, I will now start with, in detail, explain one experiment. And that is a study on the affinity electron, where we measured the electron affinity of astatine. And astatine is an element. It's the least abundant element of Earth. There is estimates of 70 milligrams in the crust of the Earth, not per ton or kilo. The total crust contains 70 milligrams. There's basically 1 atom per 100 kilo of crust of the Earth. But it's in the periodic table, and it sits down here. But basically, nothing has been done on that because it's extremely rare. So the properties of this element is not very well known. Because it's unstable, it decays through alpha. But there is an application, and that is that it's used in what's called targeted alpha therapy. And basically, so this is an element that is radioactive. If you put the element on an antibody, and then inject this antibody into the patients that have cancer, the antibody flows around, and the antibody is tailored to get attached to the cancer cell. And if that happens before astatine decays, then the alpha will be hitting the cancer cells selectively. And the good thing here is that the lifetime There's the one they use in medicine has a lifetime of 12 hours, which means that it's good time for this to float around, get stuck on the cancer before it decays. And the radioactive product is bismuth, which is non-radioactive and non-toxic. Many other radioactive isotopes have daughters that have cause new problems if you have it. But very little is known about its properties. And I said, what I will explain is how we measure electron affinity. And this is the electron affinity of the halogens. Those four are very well known. I actually mentioned a few of them. But then we have the acetylene. And when we started, this was the calculations made, the predictions. And you can see this scan from 3.8 to 2.5 EV. So they look like completely unknown. So we wanted to study this element, but we cannot go out and dig it up because it's one atom in 100 kilos. So instead we went to CERN in Geneva. And in CERN they have this big accelerator for particle physics. And this is this big, huge accelerator complex. You start down here, you produce H minus, you go into the booster, you accelerate them there, send it to the next accelerator, and you go up in circuits up to go up to big LHC where they study and they find and they boson. But then they have grown up a number of different experiments on the side. For instance, there's one very famous as the AD, the antiproton accelerator, when they study antimatter. And the experiment we did was at this solder facility. So basically that after the first booster, we take the beam and just take it out to the solder. And at the solder, we basically run the protons, the GeV protons, into the target. It's like a tube the size of a finger, filled with uranium carbide. And when the GeV protons strikes the uranium, they just split them up in every possible reaction. It's not a chain reaction, it's just a smashing reaction. And you get spallation, you get fragments, you get fission, and you basically produce the whole nuclear charge. Basically, every isotope here is produced in this violent collision. And then if you take this proton into the uranium, and then you heat that, and then put it into an ion source, you can ionize that and make it beam out whatever element, whatever isotope you want to study. And it's all the whole. So there's a lot of beam lines going out when we can do experiments. And we then build up an experiment that was carried out with Gothenburg and an detector of affinity measurements by laser photon detachment. And basically in this system, we have the beam of astatine. It comes in here, we have an electrostatic plate with bender, the ions fly, and then we apply a beam of lasers on top of this. And if the laser energy is enough to knock out the electron, well, then if nothing happens, the negative ions, the astatine ions will go in here. But if we knock out the electron, we get a neutral particle that is not deflected here. So it proceeds into this, and this is a quartz plate with a graphene layer on. And now this has an energy of about 30 keV. So when this particle hits the glass plate, you knock out electrons, and those electrons are bent out, we detect them. And then we can see that, okay, if we see electrons here, it means that we have actually photo-detached the astatine. This was extremely challenging and took many years to do this experiment. And basically the big problem here is that if we look at the numbers here, for each laser pulse, basically we have about 0.01 atoms here. So basically it's normally empty, but once in a while if you shoot laser pulses, in 1 in 100 we have an atom there. But the laser pulse contains 10 to the 14 photons. And all are hitting is the same detector. You really have to discriminate against a huge number of possible signals from the laser and see the signal. And this is actually this part of the detector you can see. picture of it. And after a lot of struggles, we got this result. This is basically that you have we tune the photon energy, and we look for the onset, we see when the production of atoms go up, and then in this way we can measure this point. And then we can extract the value of this to be 2.4, which, as I said before, was completely unknown. And the important, and that was compared with statisticians, and they calculated this. And you can see, if you compare it with your experiment, it was extremely good overlap here. And this was published in 2020. Previously, the group by Rotterdam had measured the ionization potential for astatine. How much does it cost to take away the electron from the atom? And if you have the IP and the electron affinity, you can calculate the electron negativity. And this is for a chemist like the key number for an element. Because basically, if you take two elements and want to see what kind of bond will form, but if you take the electron negativity of the two elements, if they have the same electronegativity, you get a covalent bond. If they are very different, you get an ionic bond. And this is kind of the key number for the chemists to now know how to handle this chemically. Okay, and these are the three, the David Lehmann, Julia Kors, and Anna Uva, who was the main people doing this research. Okay, and next thing I want to show, what is the time, by the way? Sorry, how much?
15 minutes.
15 minutes, okay. So then I just wanted to show you one other experiment how we can use this to show more the properties. This is basically for teaching. So when we teach atomic physics, you learn that you have the wave functions of the system. You have a spatial distribution like circular harmonics, and then you have the radial distribution. You say this is a cloud with electrons passing around. I mean, undergraduate students have never seen this because you cannot see it. You just say that's a model we use. But if I take a negative ion and apply it for it, then what I will see is that I don't get a radial distribution, but instead I will get an electron that goes away further and further. Which basically means that if you take an S electron, when you get a photon in, you send out a P wave, and the electron cloud will be random. Whereas if I take a P electron with an atom and kick it out, it will come out as an S wave. And now, if you take this, if you think about having an ion beam and a laser beam, and you interact, and you see, okay, now they fly out, then you basically create a sphere, but it doesn't expand. Then I just take an electric field and take this sphere and project it on a position sensitive detector. So we have the ion beam, the laser beam, and the position sensitive detector. And when I do that, then I will show you here, this is the for silver. So we just have a silver negative ion. I get the photons here, and I run out the electron. And it's high intensity, so I can get the atom to absorb 1, 2, or 3 photons. And on the screen, I see this. So this basically means that one means that one electron came out to this point, and if I absorb one more photon, I get larger radius, I get larger sphere. Then of course, so here you see it like a two-dimensional projection of the three-dimensional project. The student that did the work had a background in mathematics and said, we can do this really three-dimensional. He said, if we use tomography. So he proposed that we should do the same thing, but then take the polarization of the laser as rotating. And if you do that, and take a picture from every direction. And if we do that, I can now show you the video showing this. And here you can see the angle, and you can see how this shape changes. And now if you just go to the medical school and take the same proceeding that is used for tomography, then we can just reproduce this, and instead of producing the green three-dimensional, and what you just saw here is the following. So here you actually see the wave function in three dimensions plotted. And what this was expected, there's nothing new in research. I think it's a very nice way to show how we can illuminate and show a demonstration of the wave functions of the ions. Okay, and then let's see here. No, I wanted to move. Step over one part. Here, because then I just wanted to end with going back, leaving the negative ions, and going back to the experiment I showed you with the optical limitation. And this is a picture, what is the one for the picture is all. So I assume now we have trapped the sphere here. It's sitting there, and when you spray, you always produce charge on the droplets. So the droplet that you saw sitting there, even if you don't want it, it will be charged. Now, if you then in this field, if you apply an electric field, then this particle will move up and find a new position of equilibrium. And then at the same time, we can actually observe the position by taking a lens and then project that on the wall. And now it's charged, you push it up by the electric field, then we take an alpha source and approach it. And then if the alpha particle hits the droplet, it comes out electrons and it loses electric charges. And here you can see now the blue line is the electric field that oscillates to drive this particle up and down. And the green line is the position of the particle. And then you see now here you have motion that is decreasing, which basically you knock out electrons. And at some point you have no motion because now you made it neutral. But if you continue, you knock out more electrons, and then you see it starts oscillating again. And we can also see that this is we have gone from positive to negative charge because if you look here, the blue and the green is out of phase because it's a negative charge, whereas here they are in phase. So we gone from negative to positive. So then we can show actually how we interact with quantum light. And let's see. Next thing. So this was done. I can go back here. We wanted now to see, can we see the quantization here? Because the question is, how many electrons is it here? It turned out that this is about 1,000 electrons here, and found about 500 here. But can we then zoom in and improve the resolution? And if we do that, you can also see this little video, and we can see now this is the projection. So it's one droplet, it scatters from the top and the bottom, so you get two spots from the droplet. And this, on what we see on the wall, this is a simple ruler. This is a school ruler. And then each line here now corresponds to taking away a single electron. And if I now show you this video, no, this was here we were. There we go. Now you can see that it jumped, and this is in real time. And you can see through your bare eyes, filled with a cell phone. And you can see how it jumps. And you can see some steps are large and some are small. And if I show it again, you might see that actually one step is actually a single step. The problem here is we have alpha source. And the alpha source cannot out its ATD. So the alpha source cannot out many electrons. So we have to very carefully adjust the distance to get few electrons out. So the final step of this project is going on right now. And then we have replaced the alpha source with UV laser. And this is only a week ago that this was taken in the lab. And here you can basically see the position measured when we illuminate with UV light. And now you basically can see the steps here. So each step here means that a single electron is removed. I think that's quite extraordinary if you think about it. And there's a way you should demonstrate quantization of charge. And this is very much was done one of the Erasmus students, Javier Marmolejo, and Oscar Isaacson in Gothenburg. And with that, I'm coming to the end of the talk, and I'm saying, we have this collaboration, we have wanted to come. This was about a year ago, 1.5 years ago, and then Dr. Maria Solida from UNA and Dr. Alexander Dimitri from Cuba signed a memorandum of understanding for huge collaboration with our two universities. And by the way, that's the Swedish meeting that is overviewing this process. It was just like the States in Mexico in 2024. And with it now not to Linus Palmer, but the Erasmus Plus program. At the moment, we have one full-time scholarship for master studies in Gothenburg available. So if anyone in the audience, if you know about it, just let me know. So basically, for the next academic year, the scholarship covers all the costs, living costs, insurance, airfare. There's no tuition fee, and it's open for undergraduates in the 7th semester or above. And you should apply by 1st of March. We're also working on a dual degree for PhD students. That's contract is just a part of design, but we should have a program where you can sign up as a PhD student, make it part of your studies here at UNA and part of at Gothenburg University. We hope to start this also by the next year. And if you are interested in anything of this, you can contact Rika or me. Or just buy down afterwards here. And with that, I just say, this is not the reason that I'm presenting here made by me, but actually by these are the PhD students that have worked on this on the experiment I showed. And these are the funding agencies that paid for it. And special thanks to our principal who has helped me to make my slides. And here we have the next generation of students that are now working in my group. And with that, I thank you for attention.
Muchas gracias, Mike. ¿Preguntas?
Thanks for the excellent work and the excellent collaboration with UNAM in the support for the students. The image for the optical image of the wave function,
Yeah,
it was made by calculation or it was the experiment?
that is the real experiment.
That was the experiment.
Yeah.
Oh.
So you see, so I can just go back to that. Let's see if I can
Press escape.
escape. Yeah. So
Yeah.
yeah, so the experiment was done. You have an ion beam of silver ions. A laser beam comes here. You have an electric field. So when you knock out the electron, it flies up. And if it comes out with zero energy, it would go straight up and hit the center. If it has some velocity in any direction, it will go out in a parabola and hit. So that means that when in the experiment, a circle means a certain energy, and you can see the direction it went out.
Okay.
And
So what is the wavelength of this laser? What is the power of that laser?
the power is a femtosecond. It's a femtosecond laser, and then so I don't have the numbers, but it's pretty intense. I mean,
But you know the wavelength of that laser is a green or
it's
wave?
infrared.
Infrared.
Yeah, it's an infrared laser, And if I now, let's see. So just to say, no. This was too. Yeah, so that's what you see. So this is actually, so this is the electrons fly up on a screen, a fluorescent screen, and then we just have a camera sitting here watching. So that is a real camera image of the electrons coming out, which basically is about 1 eV, and the photon area is about half an eV. So that means that between each circle here you add one more, half an eV extra.
So what is more or less the size of the sample that to make this
Sorry?
experiment? What is the size of the sample that we are measuring?
We have an atomic ion beam of silver ions. So we just produce negative ions in an ion source. We make a beam of negative ions that fly. So it's very low density of negative ions that you interacting with a laser beam. But the camera can be open, so we can just sit and accumulate. And then we just, what we did was take this picture and then just take one picture at one direction of polarization, turn it 3 degrees, take a new picture, and get a stack of pictures for the tomography.
Okay, I see. Thank you.
Any other question? You can ask about the program, you can ask about the physics, you can ask about the traveling to the Atlantic, whatever you like, guys. Take advantage of Professor Hanson here. No?
Yeah.
Okay, yeah, I encourage everybody to ask questions, but in the meantime, I'll ask one. The plot that you showed with the two, from negative ions to positive ions with the alpha solars.
Yes.
And then on the right side, when you get to the positive ions, they start becoming off phase.
Yes.
Is that a cluster effect at that point, or why is that it's getting off phase? Well,
It's a, so that was the. Yeah, why they are not perfect in phase here? Yeah, this is, so one of the papers that we wrote about this was a demonstration of the simple harmonic oscillator. So that basically, if you make it, so what you do here, you have an electron and you push it up and down. And it's a damp-driven harmonic oscillator. And if we can control, so we have done this by controlling also the pressure. So without if you have basically no friction, you would get an in phase. But now since the friction of the droplet against the air makes a small delay of the response. And we can actually do that at different levels and see the complete picture of the damp-driven harmonic oscillator.
this one on the back, but not full drive.
This is not, the one I showed is in air.
In there.
But then we have done it down to 10 to the minus 3 millibar, which basically means from the point of droplet, there is no friction left. Actually, I think it's much easier to do in air because when you have when you have the laser beam here and the droplet falls down, you have a potential. Well, if you have it in vacuum, then the droplet will just jump in and jump out. So when it falls down, the friction against the air means that when it falls into the well, it doesn't come up on the other side, and it goes down and settles in the bottom. So the air friction is needed to trap it. While you trap it, then you can pump out the air and have it there started at different pressures. Here's one, yeah.
Looking at that picture, I would just call what is that this behind where you have this, you have the negative particle and we don't have the same phase.
Yeah.
And at some time I'm evidence They are high.
Yes,
And then after some time, they come back again without this
yeah.
changing the face. What is the reasons? What making this change in this environment?
So it basically means that on this side, where you are completely out of phase,
Yes.
you have the negatively charged droplet. So here you have about 500,000 extra electrons. And then with the alpha source, you take them away, which means that the amplitude of the motion goes down because the charge is less. Here you roughly have zero, so there's no response.
And then when you remove the alpha source.
It's just sitting on the same distance.
So you still have the alpha, so you
And
have.
it's not sitting there. And if it's just sitting there, you have, and it knocks out electron continuously.
Okay,
So in the beginning, you have 500 plus exact negative electrons. You lose them, they go to zero, and then you start to knock them out to make it positively charged.
so that may not a function of the activity of the alpha source.
No,
So if you increase the activity, because the activity, they give you how many particles per second that are
yeah,
coming out.
and if you increase the activity, you can do that simply by moving the alpha source closer, because then the absorption in air becomes closer. Then this will get much more rapid. And actually, the tricky thing is to be on the right distance where you get sufficiently number of alphas hitting the particle, but not too rapidly.
So there is no change in this gap.
No.
In this gap,
No.
if I increase the activity of the source, so putting it closer.
In this case, the source is simply, but we move it forward until we see that you start to see a drop. And as soon as we see the change in the number of charges, we just keep it there. And then just wait and let the alpha knock out electrons, and we see the change going from negative to positive.
Any other question? If not, guys, then I invite you to come over and talk to him in case you are shy to talk or ask questions. If you're interested in the program, let me make a clarification, and I will do it in Spanish. Si se dieron cuenta, dice que es para el grado de maestría. No es maestría en Gotemburgo. Ustedes se les pide el 70% de la licenciatura, porque lo que hace el programa es que ustedes llegan allá a escribir una tesis de maestría, perdón, pero regresan a recibir el grado de licenciatura. Cuando se gradúen de la licenciatura, tienen la licenciatura aquí, además del certificado de maestría de Gotemburgo, cual les da la posibilidad de entrar a un doctorado en cualquier universidad europea. ¿Sí? Entonces, pongan atención a eso. Bueno, entonces los invito a que vengan a preguntarle, tengan dudas, la convocatoria está abierta hasta el 1 de marzo. ¿Sí? Entonces tienen tiempo para completar su 70% de créditos. Solamente hay una posición, esta vez va a ser más competitivo. Without no more, let's thank Professor Hanstor for the beautiful talk. My name is here, I see her. That's another, one of the first 2017, I guess, 18 Linnaeus found.